Boom. Hello and welcome back to Calculus 1. We are starting chapter 3 and this is going to be on derivatives. So let's talk about the concepts. Some of the concepts from 2.1 will show here. So we'll see that as well. So what do we have? Well, let's consider a function of some kind, f of x, and that function will have this point q, and let's pick another point here, P. And if I am to connect these 2 points with a line, straight line, I would be able to find the slope of that line because I have the coordinates for point P and coordinates for point Q. So let's say that this P is at A, which means that this would be our f of A, and our point Q, let's say it's x, which would give us f of x as the y coordinate. So if you look at the slope of the line from P to Q, you would take, well, let's write the algebra formula, y2 minus y1 divided by x2 minus x1, which is what you know from your algebra course. But now if you look at the picture, since these are on the function, you can rewrite this as f of x minus f of a divided by x minus a. So this would be slope of what we call slope of the secant line. So I am going to box this and say slope of the secant line. Secant is the word with the Greek origins. Secant in Greek means to cut. So you see that this particular line cuts through the function. So it's called a secant line. And we use basic algebra to calculate this. So you will have 2 points in space, I don't know, whatever this is, 2, 5, and 7, 7, whatever. And you go and you use those points to calculate the slope of that line. Now see, the slope of the line is measuring the change. So this slope here measures the change, because if you draw a triangle like this, you see that there is change in x and change in y. So delta x is change in x, and delta y is change in y. So you can write this slope as delta y over delta x, which is exactly, you know what, let me write it here, since I already have it. There you go. So you can quickly express the change, which is just a subtraction of two values. So we can measure the change using this slope. Now this slope is something that we say is now the average change. So another one of these. This is an average change in the function. But now I am going to do something really cool. I am going to let this Q move. So I can draw a new picture. So now this Q, which has X as its X coordinate, is going to move towards P, producing a whole bunch of these secant lines. So this was going to be Q prime and Q double prime. So this is just how it moves in time. So you can calculate the slopes of every single one of these secant lines. There are infinitely many. Secant lines, right? There are infinitely many secant lines, and we can compute individual slopes for each. Except when the Q collides with P. We are going to have a line when they collide, but we would not be able to use algebra to compute the slope. So for each, and now here's the red comma, except when Q when Q and P are at the same location in space. So algebra fails at that point because your denominator, which is x minus a, becomes a minus a, which is 0, and you can't divide by 0. So we are not able to compute the slope. So we are able to compute infinitely many slopes before and after the point Q hits and passes the, so before it hits and after it passes point P, we are able to use basic algebra to compute the slopes. At the single point, which is when they collide, when they're at the same location, we cannot use algebra to find the slope. But we know that there is a line. There was a line for every point before, and then in that continuity there has to be a line at the same part. So it's easy to see if you just you fix this thing at point P, and then you see a line and a line and a line and a line, and as the point Q travels, which would be traveling this way, you keep adjusting this, and you can see a slope, a slope, a slope, a slope, a slope, and then when it passes, and it still has these slopes, so they're everywhere. So in one instance in time, right, the P and Q were at the same spot, and there was the red line there going through. The question is that line important, right? Because that's the only one that it's pain in the neck to compute. The rest are easy. You use just basic algebra. You have 2 points in space. You just subtract their coordinates and divide, and you're done. Well, this wouldn't be calculus, right? If that one case, right, wasn't what we were actually after. So we are after that red case. That is the infamous tangent line, right? And what do you think? How do we get to compute that one? Thinking of the available tools that you have. You know you can't use algebra. All you have is that algebra formula for slope. So how would you calculate the slope of the red line using what you have learned so far? Come on, should be able to do that easy, because infinitely many blue lines are leading to the red line. So what concept works in that way? Limits, exactly. Limits don't care about the point you want. They care about infinitely many cases before and after the point of interest. If my point of interest is computing the red line, and I can't, well, I don't care, because I can calculate infinitely many blue lines, which is exactly what we can do with algebra. So we can calculate infinitely many blue slopes, and we will let those slopes infer what the red one should be. So, red line is called the tangent line. Now I'm going to tell you what the tangent line is, and then we'll go from there. So, tangent line is a linear line which kisses the function at the point a f of a, and it is perpendicular to the curvature. First of all, word kisses, and then the phrase kisses the function. We use that because the tangent line is touching the function at exactly one spot, right? So, right, since there is one mouth, you can only make one kiss at a time, right? It has to be a single location, so that's why that phrasing is used. So the tangent line touches the function at exactly one spot, and wherever it touches the function, it is always perpendicular to the curvature. Now, what does that mean? Well, if you have some function, it doesn't matter what it is. It doesn't have to be a function. It could be any kind of a curve. If you pick a point, there is going to be, for a small duration here, let's say this much, there is going to be a curvature that would perfectly fit some kind of a circle that would have the radius which creates that particular curvature there. So the tangent line that you draw through this point will be perpendicular to the radius that comes in to that point. So that's what's happening. So that's what it means to be the perpendicular to the curvature. So it doesn't matter where you place this, and it also shows that the straight line would not have a tangent line, because straight line doesn't curve, and straight line has a curvature of 0. Therefore, you can't have a circle fit in that would have the radius so that the line can be perpendicular to it, and so on. So that's the notion of a tangent line, as like a concept of what it is. And we see here, so there would be some kind of a radius r, and then there's a perpendicular angle there, and all of that stuff. So now, to find slope m tangent of the tangent line, we say m tangent, and you told me it's supposed to be the limit as x goes to a of good old f of x minus f of a divided by x minus a. So this is not our final formula, but this is extremely important formula in terms of a concept, because this is where you see that you are using algebra, which is f of x minus f of a over x minus a. You're using algebra to compute infinitely many blue slopes, and then you put the limit x goes a in front of it to get the slope, which is that one slope, the red line, which is what we are looking for. So again, you can't use algebra to calculate the tangent line slope, because your denominator is 0. Remember, P and Q are at the same location whenever that line occurs. So when P and Q, which are the points that have x and y coordinates, when they're at the same location, their x values are the same, their y values are the same. So you technically have 0 divided by 0. Now, not last class, 2 weeks ago, we have seen that 0 divided by 0 is not something that is hopeless, because we said could be 1 over 6, could be 1 over 12, right? Could have a value. So in this case, we are going to have a slope. We are going to have a value for that line, and the limit is the one that helps us fish it out. So the limit is the one that gives us the value of that tangent line. Now you use basic algebra to compute this, so let's do an example of this, and then we'll upgrade and fix this. So find slope of the tangent line in a future capital TL, so we don't have to spell out tangent line every time, for f of x equals, let's say, x squared minus 6. At x equals to, I don't know, 3, whatever. All right, so this 3 is your a. So now, if I want to compute m tangent, I would need to calculate. Oh no, wait, hold on. Now we have to first fix something. We have to fix something first. We'll come back to this. Hold on. Before we start doing problems, we need to fix the formula into the different form, and then we can do that problem, and then we'll fix something else later. So 2 more upgrades to this. So what am I going to do now? To transform this formula, I'm going to use substitution. Age equals x minus a, the denominator, from where x is equal to x plus a plus age. And now we plug in. So now the slope of the tangent line becomes limit. Now instead of x, I get to put a plus age goes to a. On the other side, f of x, x is a plus age, so f of a plus age minus f of a stays as is, and x minus a, we just said that's age. So when you clean this up, m tangent is limit, you subtract a on both sides, you get limit age goes to 0 because a is cancelled, and you have f of a plus age minus f of a over age. And you better recognize the formula, because we talked about it the first day. What was this? From day one, review. The name. What was it? The name. Yes. Difference quotient. Difference quotient. Subtraction and division. Difference quotient. So now this is a different form for the problem. So now let's go and do that problem. Find the slope of the tangent line, also known as TL in the future, where f of x is, what I have then, x squared minus 6 or something, at x equals 3. So now this 3 is your a, because you are looking for the tangent line at x equals a, right? So x equals 3, meaning a is 3. All I need to do is to plug all of this stuff into my formula. Limit age goes to 0. And now I have f of 3 plus age minus f of 3 divided by age. Limit age goes to 0. F of 3 plus age, well, that has to be 3 plus age squared minus 6. Right, the function composition basics. If you have x squared minus 6 and you're supposed to replace x with 3 plus age, so it's 3 plus age squared minus 6 minus 3 squared minus 6 when you plug in 3 divided by age. Let's go do arithmetic now. This is going to be when you expand 9 plus 6age plus age squared minus 6 minus 9 plus 6 divided by age. You see the cancellations happen so that the only remaining terms are the ones with age. You can factor out an age, which leaves you with 6 plus age. Then this age cancels, and we get limit age goes to 0 of 6 plus age. And then when that age goes to 0, the answer is 6. So we found through this calculation, and this is a basic 2.3, right? Chapter 2 calculation. Basic limit. You had all of this stuff on your homework. We're not learning anything new. We're just now recognizing there's a formula. But this is the part of your homework for 2.3, this calculation. So nothing new there. Function composition. To create this term, plug in value in the function as is. Expand, cancel, factor age, cancel, and then plug in age equals 0 to come up with the final result there. These steps are going to repeat, and then you will either have fractions, you'll have square root, you'll have the square or cube or something to enjoy, but it's always the same idea. So now we found out that m tangent is equal to 6. That's the slope of the tangent line at x equals 3. And now what we are going to do is the same problem, but at a different location. Not x equals 3, x equals to 9 it is. So now, find m tangent for the same function, x squared minus 6. Is it minus 6 or plus 6? What did I have? Minus 6. And you said x equals to 9. Well, we have to go and do everything from scratch now, because he changed our location A, right? We were happy when it was 3, but now it's 9, so from scratch. So my A now is 9. Limit age goes to 0 of f of 9 plus age minus f of 9 divided by age. This will be limit age goes to 0 of 9 plus age squared minus 6 minus, and we have 9 squared minus 6 there. That's f of 9 divided by h. Limit h goes to 0. Expand 81 plus 18h plus h squared minus 6 minus 81 and then plus 6 over h. Cancellations, positive and negative 81, positive and negative 6. We see this is the check step, right? We see that the only terms that are left have h, so factor out one h. We're left with 18 plus h divided by h, so now h cancels. And we get limit h goes to 0 of 18 plus h, which is just 18. So we found that slope tangent line is 18 at x equals to 9. Perfect. How about a negative number? So you find this. Find m tangent at x equals to negative 4. Go. So what's the answer? Anyone? We have limit h goes to 0 of f of -4 plus h minus f of -4 divided by h. Plug everything in. So we get -4 plus h squared minus 6 minus open parenthesis -4 squared minus 6 divided by h. Expand everything. We have 16 minus 8h plus h squared minus 6 minus 16 plus 6 divided by h. Cancel 16s, cancel 6s. Factor out h to get -8 plus h over h. And then these guys cancel. There we go. Get the limit. H goes to 0 of -8 plus h. We get -8. So, slope of the tangent line is -8 at x equals -4. Perfect. Now what happens if I want at 10? You gotta redo the whole thing again. Exactly. Look, I asked for 3, then we went there, blah, 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 blah. Okay, got 6, great. And then you asked for 9, and then we go, blah, 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 and there's 18, okay, great. Then I say, how about the negative number, right? We're all excited. Then you totally didn't do it. And we got, well, some of you did. And then you got -8. And now I say, well, what if I want 10? And you say, I'm going to do it again? So it's not efficient, right? So how about we just do this in general terms? Instead of having our formula m tangent to be limit h goes to 0 of f of a particular a, right, which in the past were the numbers that are provided to you, how about we just say, let's use limit h goes to 0 of f of x plus h minus f of x, so we can calculate in terms of x, and then whatever x is provided at the end, we can just keep plugging that in a formula we get from here rather than restarting the whole thing. So now let's calculate all possible slopes in one shot. Calculate all slopes at once for f of x equals x squared minus 6. So now I go m tangent is equal to the limit h goes to 0, and I have my f of x plus h minus f of x over h, and we just run the calculation we are familiar from before. So I have my x plus h squared minus 6 minus x squared minus 6 divided by h. Limit h goes to 0. Expand. X squared plus 2xh plus h squared minus 6 minus x squared plus 6 divided by h. x squared, 6 and a 6, they're all gone. Our check step, only terms with age remain, so factor age out. And we have 2x plus age divided by age. Now age dies. And we are left with the limit age goes to 0 of 2x plus age, which is 2x. Look at that. We just found that m tangent is equal to 2x. So what happens at x equals 3? Slope was 6. X equals, what was the next one? 9. Slope was 18. X equals -4. Slope was -8. Remember how I wanted 10 later on? What's the slope? 20, and you didn't even run the calculation because now you have the formula which generates all of the slopes. As soon as you tell me at which point you want the slope, you are able immediately to calculate the tangent line. Now, I am really concerned with the lack of enthusiasm for this one. Because, A, efficiency. We want to be as lazy as possible, to do as little work as possible. So just run one calculation instead of 15,000. Second, did it ever cross your mind at all that you are calculating slopes of the tangent line having only one point? Did that ever occur to you? For a decade, for 10 years, you are calculating slopes of the line with 2 points. And you were told that it cannot be done differently. Now you are calculating at 1 point. Like, if that is not blowing out your mind, I don't know what your life is all about. This is like the most exciting thing you've seen in your life so far. And I'm gonna beat it in this class only once. Yeah, this is how cool this thing is. Like, you should run home and say, look at the coolest thing ever. I am able to calculate the slope of the line having 1 point only. Come on. You can't beat that. And you can't calculate it if you have no points. Right? If you have no points, you can't calculate anything. And we just made it extremely efficient because we packed all of these separate calculations that we were doing one at a time. Every time you change a point, you have to restart the problem because it was fixed to go at A. But now when you use X, you can put any value. So you calculate in general terms and you get the formula on the other end. And that one generates, for any possible value, generates the slope. Why is this slope important? Because that's what the heart of everything you ever going to learn in STEM is. Now, when I say STEM, I don't care what your individual discipline is. You are using calculus to measure the change. And this thing measures the instantaneous change. You know the one you get ticketed for when it's too high up? Yeah, that's actually this. Because as you are changing your speed by pressing gas pedal or brakes, the dial adjusts. The dial shows how many miles you are covering per hour, but it instantly changes. As soon as you touch any of the two pedals, the dial goes up or down. That dial, we'll have a lecture on it coming up. That dial shows the instantaneous rate of change, which we call speed, and that's the one that is easily seen by you as the application. Now, observe that this efficient calculation came up with a single formula at the end. What's the name of this? What's the name of this? What do you think? The name is the one and only, the star of the chapter, the derivative. Yes. This puppy here is the derivative. So what is the derivative? Derivative is a function which generates all possible tangent line slopes. Just a collection of all tangent line slopes. Collection of all possible changes that can happen for a particular function. So, the derivative is a function which generates all possible tangent line slopes. So the derivative is a function which generates all possible tangent line slopes. The formula for it is m tangent is the limit h goes to 0 of f of x plus h minus f of x over h, and the notation is f prime of x. Put this on a cloud as well, or a barbed wire, whatever you want to call it. There we go. And there it is. Can I make this more visible? I think so. Here, how about this now? I put these arrows that are pointing towards this. Over the top? Good. Yeah, I have a lot of time on my hands, as you can see. Maybe I put these angled ones here. Put one more over there. There we go. Looking good? No? Find the derivative of f of x equals 1 over x minus 2. Plug in. All right, so we just plug in a difference quotient and hit it with the limit. Limit age goes to 0, and now I have f of x plus age, so 1 over x plus age minus 2 minus 1 over x minus 2 over age. So in the first one, x is replaced by x plus age, has to keep the same form. The second one is as is. And I'll just grind through algebra. Cross multiply, get the common denominator. X minus 2. And we have x plus age minus 2. X minus 2. So now when you multiply, you get minus x minus age plus 2, everything divided by age, and you can put over 1 for double fraction, that if that helps you visually, it's okay. So now on top, these die and these die, there we go. So we are left with negative age. And then we have age times x minus 2, x plus age minus 2 when you deal with the double fraction. So now age dies, and you are left with the limit. Age goes to 0, negative 1 over x minus 2, x plus age minus 2. So now age goes to 0. That means this age drops. And we have negative 1 divided by x minus 2 times x minus 2, which is negative 1 divided by, no coughing, x minus 2 squared. And there it is. That's the derivative. So for the function f of x equals 1 over x minus 2, the derivative f prime is negative 1 over x minus 2 squared. Now, if you want to find any slope, give me the x, and I will give you the slope of the tangent line. Now you see that your x that you are providing cannot be 2, because that will create 0 in the denominator, but anything other than 2 would give you a value for the slope of the tangent line. Now if you, even though that's it's coming up in next lecture, if you draw this function, you know that there is a vertical asymptote at 2, and then you just draw, wait, what just happened? Oh, I created a new page. You just draw 1 over x, so let's say here at 1 the tangent line would hit here. Now if you calculate slope tangent at x equals to 1, you would get m equals -1 divided by 1 minus 2 squared, which is -1 divided by 1. You get -1, and you see the slope is -1 because it is a 45-degree slope that grows through each of the corners of each of the boxes, right? So it's a 45-degree slope. It's negative. Now you can also calculate exactly what the tangent line is, because you can also, you have a slope, you have a point, you can compute the y-intercept easily. So we can compute equation of the tangent line since we have slope m tangent and a point, which is your a and f of a. So you have x to y and you have m, so you can just plug everything in. So what are the specs? I have that f of x is x squared minus 6. I have that x was given as x is given as +1, and we calculated m tangent to be -1. So now I can calculate f of 1, which is 1 squared minus 6, which is -5, and that gives me a point, and I have the slope. So now I can plug everything into y equal mx plus b. Y is -5, m is -1, x is 1 plus b. So -5 is equal to b minus 1, from where b is equal to -4, and the tangent line at x equals 1 would be y equals -x minus 4. Now if you are to no, hold on, my function is wrong. My function is 1 over x minus 1. Holy nightmare. Come on, erase. So f of 1 is 1 minus 2. There we go. Which is equal to -1. So that's -1. So that's -1. And that's -1. So b is 0. So it's just y equals -x. I immediately saw I was wrong, because when I went back to the picture, it's still wrong. What's wrong now? Looking at the picture, it should be -x minus 1. So I have my function. No, we calculated slope. Slope was -1. So that's slope was -1. So we're good there. We did square it for the denominator. for the derivative. We have to calculate the y value. We have x. I just need to calculate y value, and then I use all of those in a basic. So this is what's given to us. We have the function, we have the x value, and we have the slope. Slope was calculated through the derivative. So now I plug in x value into original function to calculate the y value, because y is f of x, right? So we plug in 1, and we get 1 minus 2, that's a negative 1. So we have, no, that's good. X is 1, and y is negative 1. So now we use this equation here. So y is negative 1, slope is negative 1, x is 1, and then a b. So this is b minus 1. When I add 1, I get b equals 0. So I get x. Yeah, I probably didn't draw this nicely, because this looks like. So what I'm going to do now is I'm going to jump on Desmos and check this real quick. So I'm going to graph our original function. Original function is 1 divided by x minus 2. So that will be original function. And then I'm going to get the negative x. And as you can see, it's perfect. The tangent line, because it is touching, that's negative 1, and it's touching the function exactly at the point. So I didn't draw my 1 over x nicely. But if you graph this on the software, it just perfectly fits through. You see that 0 y-intercept on the blue line, which because b was 0. So everything fits. We have our red line to be original function. We have the blue line to be the tangent line. They touch exactly at one point, and that's at x equals 1, y equals negative 1. So if this is negative 2, then halfway it's going to be negative 1. So I have 1, negative 1, which is the point we used. Come up with the blue line anyway. So that all has to fit. All of the pieces have to fit. And that's that. That's your derivative. They give you a whole bunch of examples in a textbook that you can read. They follow those examples with a graph that shows the tangent line and the point where they touch. You can see all of the calculations. You can see the slope calculation using the limit. The same way we did in class. You have a whole bunch of other examples. Definition for m secant, which is the original one, and the m tangent, which is the slope of the tangent line. And then finally they get the derivative. And that's it. That's 3.1, Introduction to the Derivative. Bye.